Today we are looking at tutorial 3b, question 11, matrix gymnastics. Given a matrix A, which is 2 minus a half 2 over 3, check whether A is invertible, and if it is, then calculate the inverse by Gaussian elimination or using the weak 2 formula. To check whether a matrix is invertible, we need to work out the determinant. To work out the determinant of a 2 by 2 matrix, we do A times D minus BC, where for a 2 by 2 matrix, this is A, this is B, this is C, this is D. So we're doing 2 times 2 over 3 minus a half times minus a half. This gives us 4 over 3 minus a quarter, which is 13 over 12, as the determinant is not equal to 0, the matrix can be invertible or is invertible. If the determinant of a matrix is equal to 0, we say that that matrix is singular and it cannot be inverted. Now that we know the matrix can be inverted, we can go about finding the inverse. I'm going to be using both ways. So the weak 2 formula is 1 over the determinant, so 1 over AD minus BC brackets DA minus B and then minus C. If we use this formula, we will get 12 over 13, 2 over 3, 2, a half and a half. If we use Gaussian elimination, we will have to find the augmented matrix, which is the matrix A next to the identity matrix. So that gives us 2 minus a half, 2 over 3, and then 1, 0, 0, 1. And what we must now do is make A into the identity matrix. So we want a matrix of the form of IB, where B is going to be the inverse matrix. In order to do this, we can start off by making this 2 into a leading 1. To do that, we must do half of row 1. This gives us 1 minus 1 over 4 minus a half, 2 over 3. And we must also do that to the identity matrix. So that gives us a half, 0, 0, 1. Then we must do row 2 plus a half row 1, which gives us 1 minus 1 over 4, 0, 13 over 24, and then a half, 0, 1 over 4, 1. If I carry this on a new page, I now have to do 24 over 13 of row 2. That gives me 1 minus 1 over 4, 0, 1. And then doing the same to the identity matrix gives me a half, 0, 6 over 13, 24 over 13. And finally, we need to turn this element into 0. To do that, we have to do R1 plus 1/4 of R2. So that gives us our identity matrix. And doing that to the other side, we get 8 over 13, 6 over 13, 6 over 13, 24 over 13. So our inverse matrix is 8 over 13, 6 over 13, 6 over 13, and 24 over 13, which is what we will get if we expand this out. So that's part A done, using both methods. Calculate, so part B, calculate the normalized eigenvectors Rj and the eigenvalues Aj of the matrix A that are the solutions of A multiplied by Rj is equal to Aj multiplied by Rj, and verify that A is equal to this equation over here. Okay, to find eigenvalues, we need to use the characteristic of equation, which is that A minus lambda I is equal to 0. The solutions of this equation are the eigenvalues. So that A minus lambda I, so that is the matrix 2 minus lambda minus a half, 2 over 3 minus lambda is equal to 0. If we work out the determinant of this, we get 2 minus lambda multiplied by 2 over 3 minus lambda minus 1 over 4 is equal to 0. And that, when we expand that out, that gives us the quadratic equation lambda squared minus 8 over 3 lambda plus 13 over 12 is equal to 0. So our two eigenvalues would be 13 over 6 and a half. So 13 over 6 and a half. So of course the question uses a1, a2, but I tend to use lambda. Now to find out an eigenvector of a matrix A is a non-zero column vector X which satisfies this equation. A multiplied by the column vector X is equal to lambda, which is our eigenvalues, multiplied by the column vector. That's what we see here. We have the matrix A multiplied by this, in this case it's the normalized eigenvector, is equal to AJ, which are the eigenvalues, multiplied by that same eigenvector. So if we do this for a half, so when the eigenvalue is equal to a half, we get, when lambda is equal to a half, we have 2 minus a half, 2 over 3, and then x, y is equal to a half x, y. If we now expand this out, or multiply these two matrices, we get 2x minus a half y minus a half x plus 2 over 3y is equal to a half x and a half y. If we now equate the upper elements, we get 2x minus a half y is equal to a half x, which gives us 3 over 2x is equal to a half y, so 3x is equal to y. And that's the same if we equate the lower elements. So if we let x equal to 1, we get y is equal to 3. So our eigenvector would be 1 over 1, 3. If we now worked out the normalized eigenvector, we would have to find the magnitude of this matrix, of this vector, which I'll call A. To do that, we do square root 1 squared plus 3 squared, which would give us 10 root 10. So now we do the normalized eigenvector is equal to 1 over root 10 and 3 over root 10. So here we're just working out a unit vector. Cool, so this would go over here. If we do the same thing for 13 over 6, we will get the equation 2x minus a half y is equal to 13 over 6x. So of course this matrix will remain the same and we will have a 13 over 6a instead of a half, and that's where I got this equation. If we now solve this, we will get minus 1 over 6x is equal to a half y, and then minus x is equal to 3y. So if we let y is equal to 1 this time, we'll get x is equal to minus 3. So our eigenvector will be minus 3, 1. To turn this into a normalized eigenvector, we would work out the magnitude of b, which would be minus 3 squared plus 1 squared, which is again root 10. So we get as the normalized eigenvector minus 3 over root 10 and 1 over root 10. Okay, moving on to the verify. So we need to verify that A is equal to the eigenvalues multiplied by the tensor product of this eigenvector plus the second eigenvalue multiplied by the tensor product of this second eigenvector. So if I rewrite that equation, and if I now fill in all the information that we have a half, 1 root 10, 3 root 10. Okay, so these are the tensor products. So to work out tensor product, if we had a vector A and a tensor product and then vector B, we would work this out by doing A1, B1, A1, B2, A2, B1, and A2, B2, where A is A1, A2, and B is B1, B2. So the tensor product is a way of making a matrix from two vectors. Also, this should say tensor product. So if we use this formula, we get half 1 over 20, 1 over 10, 3 over 10, 3 over 10, 9 over 10, plus 13 over 6, 9 over 10 minus 3 over 10, minus 3 over 10, 1 over 10. And that gives us, if we expand the scalar constants, 1 over 20, 3 over 20, 3 over 20, 9 over 20, plus 30, plus 39 over 20, minus 13 over 20, minus 13 over 20, 13 over 60. Adding these two matrices up, we get 2 minus a half, minus a half, 2 over 3, which was the matrix A from before, so we have verified that. Moving on, part C, calculate the inverse A again, but now using the eigenvalues and normalized eigenvectors, and verify your earlier result. Okay, so finding the inverse of A. So we know that A1 is a half, R1 is 1 over root 10, 3 over root 10, A2 is equal to 13 over 6, and R2 is equal to minus 3 over root 10 and 1 over root 10. Notice how I am matching up the eigenvalues with their corresponding eigenvectors. Okay, the way to do this is to first define what a diagonal matrix is. A diagonal matrix is a square matrix in which all elements not in the leading diagonal are 0. So take, for example, the 2 by 2 matrix 2, 0, 0, 4. This is the leading diagonal. So from top left to bottom right, that arrow that goes through all those elements would be the leading diagonal. And if we look at all the other elements, it's 0. Hence, this is a diagonal matrix. If we looked at this 3 by 3 matrix, so going from top left to bottom right, this would be the leading diagonal. We can clearly see that we've got non-zero elements outside of this leading diagonal. So this is not a diagonal matrix. Okay, to reduce a matrix, let's call it A, to diagonal form, we use this formula, which goes D is equal to P inverse AP, where P is a matrix which consists of the eigenvectors of A. And what you notice is when you reduce a matrix A to diagonal form, the elements on the matrix are its eigenvalues. I've talked more about this on the video I've made on eigenvalues and eigenvectors. So from this formula, D is equal to the inverse of P, A, P, we can rearrange this formula to work out A. So in order to do that, we first times both sides by P. So that gives us PD is equal to P inverse AP, and because P times its inverse is equal to the identity matrix, we get PD is equal to AP. Now what we are going to do is times by P inverse. So that gives us PD P inverse is equal to AP P inverse. So A is equal to P multiplied by D multiplied by P inverse. Of course, this still isn't the inverse matrix of A. So to find the inverse matrix, we use this and we apply the product inversion rule. So what that is saying is if we had A multiplied by B and we wanted to find the inverse of this product of matrices, we could work out the inverse of B and then multiply that by the inverse of A. So using this rule on this equation, we have A inverse is equal to PD P minus 1 all inverse. And what you should notice is that this order reverses when we use this rule, hence inversion. So we get P minus 1 minus 1, the inverse matrix of the diagonal, and then the inverse of P. If you inverse P and then invert it again, you're just left with P. So we get P multiplied by the inverse of D multiplied by P inverse. So all of this is equal to the inverse matrix of A. So now if we define the matrix P, like I said before, P is just a matrix which consists of the eigenvectors of A. So P is going to be 1 over root 10, 3 over root 10, and then minus 3 over root 10. 1 over root 10, because these are our eigenvectors. From before, I said that when you reduce a matrix A to its diagonal form, the elements on the matrix are its eigenvalues. So the matrix D, if I write that over here, is just a half, 0, 0, 13 over 6. If I now work out the inverse of this, it would be 13 over 6, 0, 0, a half, and the determinant of this would be a half times 13 over 6 all over 1, which gives us 12 over 13. So if I add that in now, that's 13 over 6, 0, 0, a half, and I'll put the 12 over 13 at the front, and then P inverse would be 1 over root 10, 3 over root 10, minus 3 over root 10, 1 over root 10. So that's, I've swapped these two and then negated the signs of this and this matrix. And the determinant of this matrix would just be 1. So now if we multiply these matrices, if we start off with these two, we get 13 over 6 root 10, 13 over 6 root 10, minus 3 over 2 root 10, and then 1 over 2 root 10. And multiplying these two matrices, this should be a 2. That's my mistake. If we now multiply these two matrices, we will get 12 over 13, 2 over 3, 1 over 2, 1 over 2, 2. And as you can see from before, 12 over 3, 12 over 13, 2 over 3, 1 over 2, 1 over 2, 2 was the inverse matrix. So this is equal to this. So that's correct. Part D, you can do in your own time. Moving on to question 12, utility optimization. An agent has opinions about two issues with ij, with j is equal to 1, 2, and the opinions are collected into a vector sigma, which is sigma 1 and sigma 2. The agent also has evidence of each of the two issues given by eta 2, minus a half plus alpha, where alpha is a real number. The utility function of this agent is this equation over here. Find the first order conditions, determine for which condition on y they are solvable, and solve them to find the local optimum sigma. Here, what I'm first going to do is write this whole equation out. So sigma is a vector which is sigma 1, sigma 2 is equal to eta, which is 2 and then minus a half plus alpha, and sigma is sigma 1, sigma 2, minus a half, sigma 1, sigma 2, 1 minus y, 1, and then sigma 1, sigma 2. If we now expand everything out, so with this we have to use dot product, we get 2 sigma 1 minus a half sigma 2 plus alpha sigma 2 minus a half. If we multiply these two first, we get sigma 1 minus y sigma 2, and then minus y sigma 1 plus sigma 2. And if we multiply everything out now, we get minus a half sigma 2 1 plus 1 over 2 y sigma 1 sigma 2 plus a half y sigma 1 sigma 2 minus a half sigma squared 2. If we now find the first order conditions, so sigma, so if we now find the first order conditions, we get the partial derivative of the utility function with respect to sigma 1, which is equal to 2 minus sigma 1 plus a half y sigma square sigma 2 plus a half y sigma 2. Doing the same thing with respect to sigma 2 now, we get minus a half plus alpha plus a half y sigma 1 plus a half y sigma 2 minus sigma 2. If I now write that as a column vector, we have 2 minus sigma 1 plus y sigma 2, and then minus a half plus alpha plus y sigma 1 minus sigma 2. This is also equal to 2 minus a half plus alpha minus sigma 1 minus y sigma squared minus y sigma 1 plus sigma squared. So now I can also write this as eta, because this is the exact same as this, minus 1 minus y 1, and then sigma 1 sigma 2. So our first order conditions would be eta minus the matrix M, so I'm going to call this M, and then the vector sigma. Now we need to determine for which conditions on y that they are solvable. So if the determinant of the matrix M is equal to 0, there will be no solutions. So if we now work out the determinant, so that of 1 minus y 1, we get y minus y 1 minus y squared is equal to 0. So that means we get two solutions. Y is equal to 0. So y is equal to 1 and y is equal to minus 1. So if I write this over here, therefore y cannot be equal to plus or minus 1, because if that is the case, the determinant is 0, and hence there will be no solutions. If we now try and find the local optimum, we need to equate the first order condition to 0. So eta minus the matrix M and then the vector sigma is equal to 0. We get eta is equal to matrix and then sigma. If we multiply both sides by the inverse of m, we get m minus 1. Eta is equal to sigma, because m times its inverse will be the identity matrix. So this is what we need to solve for to find the optimum. If I jot that down over here, so the inverse of the matrix M would be 1 over 1 minus y squared, and then 1, 1, y, and we multiply that by 2 minus a half plus alpha. So then we get 1 over 1 y squared. And when we multiply these two matrices, we get 2 minus a half y plus alpha y, and 2y minus a half plus alpha. So our local optimum would be 2 minus a half y plus alpha y divided by 1 minus y squared. And the other one would be 2y minus a half plus alpha divided by 1 minus y squared. Hopefully that makes sense. Part B. Is there a value of alpha such that the optimum value of sigma 1 is equal to 0? So to work that out, we need to do 2 minus a half y plus alpha y. So this, and equate it to 0. When we do that, we get 2 minus a half y plus alpha y is equal to 0. And then we can write y minus a half plus alpha is equal to is equal to minus 2. And then we get alpha is equal to minus 2 divided by y. And then we need to move the half to the other side. So we get plus a half. So the result would be minus 2y plus a half. Part C. Determine the nature of the local optimum and whether there is a restriction on the allowed values for y if we demand the local optimum to be a maximum. So we need to work out the Hessian. The Hessian is defined by the second derivative of sigma 1 squared, the second derivative of sigma 1, and we partially differentiate that with sigma 2. We reverse the order over here, and then we work out the second derivative of the partial of sigma 2 squared. So that's the Hessian. If I jot down the first derivatives, we had 2 minus sigma 1 plus y sigma 2, and we had minus a half plus alpha plus y sigma 1 minus sigma 2. If I work out the second derivatives, differentiating this with respect to sigma 1 again, we will be left behind with just minus 1. Differentiating this now with respect to sigma 2, this goes, and we're just left with y. Now if we move on to this, differentiate this with respect to sigma 1, this goes, because they're all constants, and this goes, and we're just left with y. And if we differentiate this with respect to sigma 2, this goes, and we're just left with minus 1. So that is our Hessian. To determine the nature of the local optimum, we need to find the eigenvalues of this Hessian. To do that, we have to use the characteristic equation, which is that h for Hessian minus lambda I is equal to 0. So that of the matrix H, minus 1 minus lambda, y minus 1 minus lambda is equal to 0, and then minus 1 minus lambda minus 1 minus lambda minus y squared would be our characteristic equation. If we now solve this, we get minus 1 minus lambda all squared is equal to y squared. So minus 1 minus lambda is equal to plus or minus y. And then minus lambda is equal to plus or minus y plus 1. And then we've got lambda is equal to plus or minus y minus 1, which I'm going to write as minus 1 plus or minus y. Okay, so these are our two eigenvalues. So from this, we can see that when y is greater than 1 or y is less than minus 1, one value of lambda is positive and the other is negative. When this is the case, we have a saddle point, and when we have minus 1 and then y less than 1, so when y takes a value between minus 1 and 1, both values of lambda are negative. This means that the Hessian is a negative definite, and therefore the optimum is a local maximum. So, determine whether there is a restriction on the allowed values of y if we demand the local optimum to be a local maximum. This would be those conditions. Cool. Hopefully that made sense.